Hi everyone, welcome back. So the last several sessions we were together, we were talking about triangles. We're not done talking with triangles, but we're going to do something different with them today. And we're going to use them to help look at angles in polygons. A helpful website is going to be mathsisfun.com/geometry/polygons.html. If you're in front of me today, I want you to please make sure you have that open on your cell phones along with your favorite calculator app, so that because we're going to be multiplying numbers and they're going to get really big really fast. And I can barely handle like one digits multiplying together. As soon as it gets beyond two, I'm like, no. I can't do it. So please have your calculator apps to help me with those number crunchings. And then have this out and available so you can scroll. Alrighty, before we get into the actual lecture, I have two vocabulary terms to define for you. The first being a polygon. Have you heard the word polygon before?
Yes.
What do you think it is?
A plane shape.
A shape with more than 3 sides.
A shape with more than 3 sides. I heard someone say a plane shape
And it's
with
closed.
straight sides.
It's also closed.
And it's also closed. All right, so we'll write down plane shape. Now, when we say plain, we don't mean like undecorated. We don't mean like boring. We mean that this is a shape that can be drawn on a plane, which means it is flat, it is two-dimensional, it does not curve. So take a moment and head to our new favorite website, and we'll take a quick look at what it says. Two-dimensional shapes. Can you read it? Is it bright enough?
Yes.
My cell phone? Okay. It's made of straight lines, and the shape is closed. That means that all the lines connect up. So the one on the left is totally a polygon because it's all straight and closed. The middle one is not because I got a curvy in it. And the last one isn't because I have this big hole. Okay. The next one that I want to go over with you is regular polygons. Regular polygons are all equal sides, all equal angles. And so in your notes, I'd like you to please write regular polygon. And we're going to use the big fancy math terms for all equal sides, all equal angles. So we're going to say equilateral and equiangular. Okay. So in the course of today, when we're looking at the examples and we see an example that says such and such is a regular polygon, we mean all the sides are congruent, all the angles are congruent. So here's some examples of what it's going to look like. Otherwise, we'll call it irregular or just is a polygon. You're also going to need to be able to determine the difference between concave and convex. Concave just means that all the corners stick out, and convex means all the corners stick out, and concave means one of the corners might be crushed in. Okay? This website's also going to go into stuff like simple and complex. We won't be using that, but just so that you have it in the back of your head, simple polygon is one where there's one polygon, and a complex is one where there's lots of polygons. 2 or more. The sides cross, and it makes a bunch of polygons and weird shapes. Okay, so here's a couple more examples for you. Some irregular, some concave, and a complex. Okay, now that we have those defined, let's get into today's lecture. A segment that connects the non-consecutive vertices of a polygon. These are the corners that don't go one right after another, that we've skipped a corner. The segments that connect those skipped corners are called diagonals. This is supposed to be an A. Diagonals. And by drawing all of the diagonals from one vertex of an angle, it separates, it cuts the polygon into n minus 2 triangles, where n is representing the number of sides or angles in your polygon. And it's going to cut it into that many triangles. Okay, so let's take a look at some of the shapes. We're going to draw some diagonals and count how many triangles we end up with. Okay, so I'm going to zoom it in. All right, I have a triangle. How many sides does the triangle have? 3. We can easily count them, 1, 2, and 3. And now we want to draw a diagonal. Remember, that means we're going to go from a vertex to a corner, skipping a corner, so that we're not drawing over its sides. I can't do that on a triangle because every corner is consecutive. So I'm done. I've drawn all the diagonals. I've drawn none. And I have one triangle. All right, we're going to look at the quadrilateral. How many sides does a quadrilateral have? 4. The prefix quad tells me 4, and I can count the outside edges. 1, 2, 3, and 4. So this quadrilateral has 4 sides. Going to draw the diagonals now. Start at a corner, and I'm going to go to the next non-consecutive. I'm going to skip a corner. I can totally do that now. 1 diagonal to draw, which means I have 2 triangles. Pentagon, how many sides? 5 sides. 1, 2, 3, 4, 5. Now I'm going to take a moment here and remind you that this picture is not representing a 3-dimensional object. Those lines that you see right here are the diagonals. They're going from one corner to another corner. They're not trying to tell you that the shape is popping up off of the page. Okay? That's why we made it very specific that these are polygons, and polygons are plane shapes. They're flat shapes. Okay? They're not 3-dimensional. Yes? Okay. So I could draw 2 diagonals. How many triangles? 3. Good. The hexagon, how many sides? 1, 2, 3, 4, 5, 6. I can draw some diagonals. And how many triangles do I end up with? 4 of them. Notice the pattern. The pattern said n minus 2 number of triangles. In a triangle, 3 minus 2 is 1. I have 1 triangle. In a quadrilateral, 4 minus 2 is
2.
I have 2 triangles. In a pentagon, 5 minus 2 is I have 3 triangles. In a hexagon, 6 minus 2 is 4 triangles.
Wait, why can't on the quadrilateral, where the 1 is,
Mhm.
that angle, why can't you connect it to the 2?
I totally could. But then I'd be counting this triangle and this triangle. Okay? To count the triangles, it's just from one vertex to all the other corners that don't make us cross over a side, the non-consecutive. And those are the triangles we count.
Oh, okay.
Yeah, we don't count triangles by drawing just diagonals everywhere and then have a million triangles. Okay. This lets us find the sum of the measures of the interior angles of a polygon. And we do that by adding the measures of the interior angles of all of those triangles that we just cut. What's the interior angle sum for a triangle? 180. So in a triangle, I have 1 triangle, so I have 180. In a quadrilateral, I have 2 triangles, and so 180 times 2 is
360.
360. Some people can do that in their head. In a pentagon, I have 3 triangles, so 3 times 180 is 540. In a hexagon, I have 4 triangles. 4 times 180 is? And so this formula down here, this n minus 2 number of triangles I can cut my polygon into times 180 gives me the interior angle sum of every polygon ever in the whole wide universe. I knew that bell was going to ring. I had a feeling, so I just wanted to wait and not talk. The The theorem that talks about the interior angle sum of a polygon says this. The sum of the interior angle measures of an n-sided convex polygon. Remember, convex just means that the corners are all poking out. None of them are crashed in. And n is the number of sides that you're looking at. Is the number of sides minus 2. Whatever you get from that times 180. So in parentheses n minus 2. Now the parentheses 180. Let's practice using this a few times. Alrighty, come down with me. Scroll down to the bottom of the page. Number 1. A convex polygon has 13 sides. So n equals
13.
Beautiful. We are trying to find the sum of the measures of the interior angles. So we want the sum of the measures of the interior angles. We have a formula for that. Yes, we do. I'm going to scroll up so that's on screen. There's my formula written very badly. It says the number of sides, which is n minus 2 times 180. The number of sides is 13, and so 13 minus 2 times 180 will be my angle sum. That is 13 minus 2 is 11, so 11 times 180 is 1,980.
That's a lot of angles.
That's not how many angles there are.
I mean, the sum of the.
That's the sum of the measures of the, it's a lot of degrees. Do you want to see another one, or is that enough?
No,
Another one? Okay. If you're feeling comfortable with that, go ahead and head to the assignment. You can find a problem that looks just like that. I'm going to look at number 3 on our practice problems. Number 3 says, find the sum of the measures of the interior angles of each convex polygon. And then it says, decagon. And I go, how many sides does a decagon have? 10? 12?
It's 12.
13? I don't, you know what? I have this website. I'm going to zoom, I'm going to brighten this just a little bit. Alright, so I'm going to go to the website, and I'm going to go down toward the bottom. It says names of polygons, and I'm going to scroll until I find decagon.
Oh wait, no, it's 12. Oh wait, no, it's 10.
It's 10. It's 10. Deca is 10. Deca, D-E-C, dec. It's where we get our Spanish word diez. It's where we get our month name December.
December is 12.
What December's 12?
You're right. Story time.
Oh no, it's because of the Caesar guy, right? And he added those 2 months.
So
For
long
African.
time ago, back in the Roman Empire, we're talking like 2,000-ish years ago, there was 10 months. Month 1, month 2, month 3, month 4, month 5, month 6, and then they went month 7. We're tired of naming these cool names, so we're going to have September for month 7, and October for month 8, and November for month 9, and December for month 10, and that was their whole year. And then this dude came along and went, yo, I'm the shizzle. I'm so awesome, I want my own month, and it's going to be named after me. And they went, Julius, really? You can't just, he goes, I am Caesar, it will be done. And they went, fine, don't kill us. And they slipped his month in right before September. And we ended up with July. A little while later, another Caesar went, dude, that was cool. I want to do that. I want a month. And they went, Augustus, come on. Fine, you can have a month too, right after Julius's month, but that's it, no more months. This is getting out of hand. That's it. So they added in July and August, but didn't bother to rename September, October, November, December. So it blows my mind when I try to think of decagon, 10, and December, like,
No,
it hurts my head.
maybe
I know that.
Don't
That's a Tumblr.
Tumblr is a cool, cool place. All right, so what was N then?
It was a post.
10. All right, we're going to go ahead and go into our formula then. This is just me writing down and keeping track of everything that we need to do on this one. So not really doing anything special. I do need help with 8 times 180 though.
Like 1,400 and something.
Like 1,400 and something. Okay? 1,440, and I got that from 2 different people, 2 different sides of the room, so E's confirmed. Really easy? Really easy to overthink. Don't overthink it. Okay? Alright, let's step this up one little bit. Come back to the first page of your notes. We're going to look at number 2. This one? Oh, he's got it for you. Thank you. All right, number 2 says the measure of an interior angle of a regular polygon. So the measure of just one interior angle of some sort of polygon is 120. But I'm told this thing is a regular polygon.
All sides of it.
All sides are equal. All angles are equal. So I know that however many sides or angles this thing has, all of those angle measures are exactly the same. The formula that I have gives me the sum of all the angles added together. If I have a grand total, and I want to evenly distribute that grand total amongst some number of things, what do I need to do to that grand total?
Divide.
Divide by
How many that grand total is.
the number of things I'm trying to distribute this grand total to, yes? What's the number of things I'm distributing this grand total to?
Like 20.
That's the angle measure.
Oh.
How many angles am I distributing it to?
2.
I don't know, right? Because the number of angles is the same as the number of sides, and I'm being asked to find the number of sides. But what symbol do we use to represent the number of sides? Say it. You could use X. Right now we're using N for number. But I like that you went to a variable. Nicely done. We're just using the variable N for number. It looks weird. We're dividing by a letter. That letter could be any number, including 0. Are you nervous yet? Don't be, because think about it. You have a polygon with 0 sides. We don't have a polygon. We have a nothing, or we have a squiggle. Like, it's not a polygon. So then we wouldn't use this formula, and we haven't broken algebra.
We know it at least has 2 sides.
We know it probably has at least 3 sides. Could there be less than 3 sides? I don't know. Let's not get that philosophical yet. Okay, so then we're assured that this formula will give us the measure of one angle in a regular polygon. What is the measure of the angle in this regular polygon? 120. I heard it very soft over here with a, I'm not sure if I'm right, but you are. And now I can solve this equation for n, the number of sides. Are you panicking yet?
I'm gonna need another example.
It's okay. We'll try to find as many as we can. I have a fraction. It's in an equation. How do you get a fractions in an equation?
Multiply by the denominator.
Multiplied by the denominator. Okay. All right, boss, I'm going to do that. I'm using square brackets here just so it looks different from the parentheses. I don't like too many round parentheses next to each other. You use whatever shape parentheses you like. I'm using boxes. Alrighty, I have multiplied both sides by n. When I do, on this right-hand side, the multiplication by n and the division by n are going to cancel, and it leaves me with just the numerator. Now, no more fractions. I am happy.
And then you distribute 180.
Let's distribute that 180. You could divide by the 180 here, because the 180 is being multiplied, but if you do that, you run the risk of introducing more decimals and fractions. And we just went through the trouble of getting rid of them, so why introduce them again? All right, distributing it is.
Wow.
Continuing to solve for n, I need n all on one side of the equation,
So we subtract.
the left or the right side.
The right. Oh,
Okay, he wants the n's on the right-hand side. let's do it. That means I need to get rid of it here on the left-hand side. And 120n minus 120n leaves me with how many n's?
60 and
120 minus 120?
0.
oh, I
So
thought
just
0. I have no more n's on that side. You were already thinking over here to this other side with 180 minus 120 is 60. That's okay.
Yep.
All right. I'm trying to get n by itself.
Then we add 360 to the other side.
We can add 360 to both sides to get rid of the 360 on the right-hand
And
side.
then we divide 360
And when
by
I do
2.
that, I have 360 equals 60n. And then as he was mumbling over there, which is completely okay, we're going to divide by 60 on both sides and be left with,
6.
equals
our polygon has 6 sides.
Whoa! That was a lot of work.
We'd had another example requested, so on the second page, 6, 7, and 8 are the exact same way. Please pick the one you'd like to see done, 6, 7, or 8. 7. If you're already feeling really comfortable with this, feel free to go into your assignments, find problems like this so that you can work on it with us with different numbers. All right, the measure of the interior angle of a regular polygon is given. We had a formula to find the measure of a single angle. It came from our angle sum being divided by the number of sides, number of angles in our polygon. So there's where I'm going to start. I'm going to get rid of the fraction in the equation by multiplying both sides by the denominator. That's going to turn the left-hand side into 160n and the right-hand side into n minus 2 times 180. Again, as I look at this, I want to distribute. I could divide the 180. But if I divide the 180, 160 divided by 180 is not a whole number. And so that's going to make things weird. So I don't want to do that. I don't want more fractions. I'm going to go ahead and distribute. Subtract something from both sides. Okay. You could subtract the 180. I had a call to subtract the 160. Both of those things are correct things to do. Then we're going to add 360 to both sides. I'm going to do that over here and kind of ignore this one for a second. And then, okie dokie. And the number of sides in my polygon is?
16, isn't it?
16. 16 times 2 is 12. Not quite enough.
Wait.
I'm waiting.
18.
18. Calculator app? I'm okay with that. That's why I said calculator apps today, guys, because, oh my god, these numbers are getting really big and we have to multiply and we have to divide. And, Feeling better about these?
Yes.
Good. I want to look at number 9 before we move on to our next theorem. Because number 9 is weird. The direction is to say find the value of x, and then they give me this thing.
Well, they all have to equal to.
I don't know anything about this figure, except that all the sides are straight. Which means this is it's a polygon.
But is it a regular polygon?
I'm not told. That's a really great question. His question was, but is it a regular polygon?
Because you can't assume.
I don't know. Yeah, I can't assume. It certainly doesn't look regular. It looks like it's all sorts of sizes, but maybe they just are really bad at drawing regular polygons. But they don't tell me, so I can't assume. So I'm going to use the only other thing I know about polygons, and that is my formula to find the sum of all of them added together. Because if I can find the grand total of all of these added together, then this angle measure plus this angle measure plus this angle measure plus this angle measure plus this angle measure is going to equal whatever I get when I figure out this thing.
Oh,
So that's what I'm going to do. How many sides does this polygon have?
1, 2, 3, 4, 5.
Five.
It's a pentagon.
It's a pentagon. It's a, yeah, pentagon. I don't know what I was going to say. 5 minus 2 is 3, and so we're looking at an angle sum of 3 times 180. Help, the numbers are too big. 540. Okay. All right. I'm going to scoot over now, 540, because 540 is whatever I get when I take this angle and add it to this angle. When I add it to this angle, when I add it to this angle, when I add it to this angle. And that equation looks intimidating. Because it's so big. It's a big equation, there's a lot going on. But relax. We're just going to combine some like terms and see if we can't make this thing look smaller. I'm going to start with my x's first. There's a thing with x, and 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 there's a thing with x. Notice how I included the signs in the boxes with them. So I have 7 plus 4, 11. Plus 6 more, 17. Plus 5 more, 22. 21? 23. Someone do 17 plus 5, please.
18, 19, 20, 21, 22.
22 plus 4 more is 26x. All right, gonna do the exact same trick, but this time I'm gonna do it to the numbers. All right, 10 plus 10 is 20. Minus 5 is 15. Plus 5. And I'm not touching the right-hand side. Oh, that equation looks so much better. Now what?
Minus 20 to both sides.
All right. Now what? Divide by 26. And when I divide by 26, I get 20. Okay. If you say so, boss. That's it. These are the more complicated ones, not because they're hard, but because there's a lot of steps. What's the first thing that we did?
We found this.
We counted the sides, and then we used the number of sides to
Find the measure.
angle sum.
Find this.
And once we got the angle sum, we
Equaled it to.
equaled it to the angles, to the sum of all the angles. That thing plus that thing plus that thing plus until we were done. Yeah? And then we solved for x.
Yes.
All right, let's cover the last theorem for the day. This one should go really fast. We're doing okay on time. Just as we found a relationship with the interior angle measures, so too is there a relationship with the exterior angle measures. Please note those exterior angles are those sitting outside of the angle, just like we had the exterior angle in a triangle. But this says that the sum of all of those exterior angles is going to equal to something. Drum roll, please. 360. That's it. There's no formula. There's no letters to deal with. It's 360. Do we care how many sides there were?
No.
Do we care how many angles they were?
No.
Do we care whether this thing is regular or irregular?
No.
As long as it's a convex polygon, that means all the corners are pokey out, none of them are pokey in, then we know that when we add them up, we're going to get 360.
So,
Please, yes.
how do you form the exterior angles if it's supposed to be a closed figure?
Like that.
What?
You take a side from one vertex and you extend it past the other vertex and you call this little angle right here the exterior angle. That's it. Please join me, page 2 of your notes. We're on problem number 10 and it says find the sum of the measures of the exterior angles, where you have one at each corner, of some sort of convex 27agon. That's literally how you say the name, 27agon. And it's because no one wants to go in to this chart and go 27 and icosaheptagon. Like no one wants to go there. So then we just gave up and we went 27 gone. Okay. Exterior angle sum, 27 gone. What is it? Look at the theorem.
180.
No, it's 360. That's it.
Simple math.
Super easy. Do you need to see another one like that?
Easy math.
Oh wait, so just no matter what it is.
No matter what it is. Which means look at 12 through 14. The sum of the measures of the exterior angles of each 360. I don't care how many sides these things have. No one cares. It's always
But
360.
that's a convex polygon.
Yeah, convex. It's always going to be convex.
What about if it's
Different rules. Can't deal with it. Yeah, we don't have anything for that. All right, let's look at number 11. And this is our last example. Find the measure of each exterior angle of a regular hexagon. All right. Exterior angles, we want the measure of exterior angles. I know exterior angles of polygons is always 360. Hexagon has how many sides? 5, 6. I don't remember. I'm going to come to my list. I'm going to scroll around. I'm going to look for hexagon 6. All right. Now I want regular. What?
Equilateral or equiangular?
Equilateral, equiangular. All the sides are equal, all the angles are equal, including the exteriors.
So we just divide 360 by 6. 360 divided by 6. 60. Every angle is 60.
Poof, done. That's all I had for you guys today. Thank you very much.
Easy math. In the next episode of Geometry Classroom!
Someone tickle him!